Welcome to PPI's webinar today regarding safeguarding plastic piping systems after wildfires. This has obviously been a topic that has come up here in the last couple of weeks given the tragic fires, mainly in California, but there are fires in other parts of the world as well. And we're hoping today to give you access to some of the PPI resources, give you some background on those resources. And again, if you would please keep yourself on mute, keep yourself off of video. And at the end, we will open this up for question and answer. In the interim, if you have something you don't want to forget, if you would just please put it into the chat and I will monitor that for Patrick. So with that, Patrick, do you want to go ahead and introduce yourself and start the presentation? And I'll just keep an eye out on chat, and Kelly and I will tag team muting folks if they come on and can't follow the rules. So welcome everybody, and Patrick, take it away.
Thanks, David, and good morning and good afternoon, wherever, depending on where you're at. So as David indicated, we decided to put together this short webinar, and it should take less than half an hour, and we should have plenty of time for questions at the end. And we will be posting the webinar on the member portal website soon after the webinar. I will apologize right now that I have the remnants of a cold and have been coughing, so if I mute myself for a minute, it may be because I'm having a little coughing fit. So, our goal is to educate our members on the issues of wildland-urban interfaced wildfires. That's a mouthful. That's why we call it a WI wildfire, and I'll simply call it wildfire for this presentation. We'll look at the impact that the wildfires have on plastic piping. We want to highlight the PPI resources for members and the public. In this webinar, we'll first describe what a wildland-urban interface wildfire is and what resources we have for you on our PPI website. We will then get into some of the recommendations as to what to do with piping that has been involved in a wildfire. We will also look at the PPI recommendations for piping that was installed above ground and located below ground. We will then address some of the reports of piping contamination following the wildfire and what we've learned related to that contamination, addressing what is true and what is false or dubious. We will have time for a Q&A, and we will highlight some of the potential next steps. So what is a wildland-urban interface wildfire? Well, it's a fire that starts in a wildland and spreads into an urban area. A wildfire in the forest is very intense and fast-moving. It burns the materials that are on the ground quickly. That's the fuel, and then moves on. The heat penetration into the soil is very shallow because the fire is so fast-moving. An urban fire is slower moving, and lingers longer due to the higher fuel loads, so cars, houses, etc. And for that reason, the heat penetration into the soil is somewhat deeper and over a longer period of time. So PPI has two publications that we want you to be aware of. That is, I'm getting some background noise there. Okay, so please mute yourself. So PPI TR51, that was published in 2020, and it's entitled The Investigation of Benzene in Drinking Water Following the Camp Fire in Paradise, California. So back in 2019, following the wildfires that decimated Paradise, which was also called the Camp Fire, there were reports in the news of contaminated drinking water caused by plastic piping. PPI staff visited Paradise and interviewed the lead water officials restoring water to the town. This technical report summarizes the findings from our investigations, and it includes some surprising information that had not been reported in the news. The second document was published last year following the fires in Lahaina, Hawaii. We felt a guidance document was needed, so PPI Recommendation I, called Guidance on Restoring Potable Water Piping Systems Post-Urban Wildland Interface Wildfires, it's a mouthful, and provides basic, simple, straightforward guidance on how to treat plastic piping following a wildfire. The recommendations on the next few slides are directly from recommendation I. So above ground, what's the impact? So by above ground, we mean non-buried exterior piping and inside building piping. In the case of it being exposed to fire, plastic piping will char, melt, deform, or burn. Even metal piping may be affected, as we saw evidence of premature corrosion, and metal that could also have been affected in visible ways. So the short and long-term performance of the piping following heat exposure is unknown. And as you can see in the pictures of the above ground service connections highlighted here, you can see examples of plastic piping that have been affected by the fire. You can see the charring, you can see the deformation in the piping. You can also see in this bottom picture evidence of a brass valve that melted due to the heat. And the handle is also corroded. So what does PPI recommend in terms of above ground piping? Well, recommendation I says potable water piping systems and components that have been exposed to directly to high heat or flames should be replaced. This recommendation applies to all piping materials, including metallic piping. Regardless of the material, long-term functional capabilities may be compromised. If in doubt, replace it. So what about below ground? We may need to, in this case, to distinguish between pipe that transitions from above ground to below ground, and from very shallow buried pipe to deeply buried pipe. The impact of the wildfire will depend on the depth of that piping and the type of cover. Piping that transitions from above ground to below ground will likely be damaged by heat and fire. Exposed piping below ground may melt or burn. For example, in a meter box. And this picture to the right shows you a plastic meter box with some detritus in the box here. And below is a meter box that was hit by fire and melted over the meter and the piping. Very shallow buried piping may melt, but it's not likely to burn because it's completely covered. And the common practice is to bury pipe below the local frost line. So properly buried piping at depths greater than 12 inches should not melt or burn. So what does PPI recommendation I say? It says any piping or component buried less than 12 inches, as well as piping transitioning out of the ground, should be examined and considered for replacement. Any piping or component showing direct heat exposure as evidenced by melting, distortion, leaks, or smoke staining should be replaced. These recommendations apply to all piping materials, including metallic piping. Regardless of the material, the long-term functional capabilities may be compromised. If in doubt, replace it. Now let's talk a little bit more about that piping that is buried more than 12 inches. Studies have shown that deeper piping should not be affected by the heat that is being conducted from the surface through the soil. The studies show that the heat penetration, even in the urban environment, is very limited because the temperature is heavily attenuated with soil depth. This is illustrated in the lower figure, which shows that the inner wall temperature across the top here, and the burial depth along the left here of the chart. And these different curves here represent the intensity and type of fire. You can see that from the chart that at very shallow burial depths, that would be up here, that the temperature can be quite high, up to 600 degrees C or 1100 degrees F or higher. Thus, those kinds of temperatures are going to melt or damage the pipe, of course. But as you increase the depth, the pipe wall temperature decreases quickly. And at 0.3 meters, which is 1 foot or 12 inches, you can see the pipe wall temperatures reach under 100 degrees C for a short time in the worst case scenario, and significantly lower temperatures in most cases. So typically a service lateral that's buried a foot or deeper and a main that's buried even deeper really isn't going to see elevated temperatures. And as per the evidence following the Paradise, California wildfire, it was observed that the mains were unaffected by the heat, and most surface lines were unaffected by the heat. Meter boxes and the connections within the boxes were often damaged because they were very shallow. The boxes themselves were made of plastic that melted and burned, as I showed you in the last pictures, which in turn melted and ignited the piping within. So what about the reports of contamination? Post the Paradise and Santa Rosa fires, actually, there were reports of potable water coming from pipes contaminated with benzene and other volatile organic carbons. The concentrations were above the EPA health limits for drinking water. It proved very difficult to flush these service lines to effectively reduce the concentration of those contaminants to safe levels. We don't dispute these observations. There were also reports that plastic piping was able to absorb and then release contaminants back into the water, and this probably is the case. There are also reports that the source of contaminants was the burning of plastic piping, and this is where we take exception and dispute those reports. So let's look at our experience or from our investigation of the Paradise, California fire and what is detailed in PPI TR 51. So, and this really applies to both the Camp Fire in Paradise in 2018 and the Tubbs Fire in Santa Rosa, also in California, in 2017. Both were basically massive wildfires that spread into and decimated residential areas. Both these towns are located in foothills in California. In both cases, the piping systems lost pressure and water was siphoned out of the piping system. This is called a negative pressure event. Sometime after the fire, when they were trying to put the water system back into service, they tested the water and found trace levels of benzene and other VOCs that were above EPA health limits. The limits were exceeding both the mains and service lines. Interestingly, the location of the contamination appeared random, and neighboring buildings could see completely different results. Importantly, contamination was found in water that was coming through both plastic and metal water piping. To try and resolve the situation, they started flushing the piping. The flushing the mains resolved the contamination within the mains, reducing any contamination below acceptable limits. However, flushing the surface lines proved to be often impractical, as contamination would reappear once the water was allowed to remain stagnant in the pipe for a little while. The town of Paradise's solution was to replace all service lines with AWWA C901P 4710 water service pipe. And to protect the water systems in the event of future fires, they installed backflow prevention devices on all service lines that would stop that sort of suction event occurring should the same negative pressure event occur. So let's examine a little bit some of these claims further. So starting with the claims that the benzene and VOCs was coming directly from the pipe heating and burning. This claim has been promulgated by Professor Andrew Wilton of Purdue, who, in my opinion, ignored other potential sources for the contaminants. He also did some completely unrealistic lab experiments to test the theory. In this test, he burned plastic piping samples, and unsurprisingly, these did show minor benzene VOC generation when taken to temperatures over 300 C or 570 F for extended periods of time. Note that these temperatures are well above the melting temperatures for polypropylene and PVC, etc. He did admit in his paper that the quantities of VOC generated and extractable in his experiment couldn't explain the observed quantities of those contaminants seen in the water distribution system. He basically ignored this inconvenient fact in his findings and continued to promote piping as the source of contaminants. More recently, he's acknowledged that other sources may have contributed, but continues to promote that piping as a significant source of that contamination. You can see in the figure on the screen that's taken from his paper the pipe after he heated the samples at 200C, 300C, and 400C. It was around 300C that he started to see some benzene generated. And you can see the pipe is evidently melted and would be non-functional anymore. So it's rather academic whether uh, the pipe is producing benzene at that temperature. Subsequently, Professor Erica Fisher and Brad Wham did some experimentation. And in that experimentation, they confirmed that, yes, you can produce VOCs at elevated temperatures. They determined that at 380 C or 700 degrees F for PVC and above 490 F for HDPE, you would potentially start to see some VOCs. So these are higher temperatures than reported by Welton. But more importantly, they did an extensive analysis of the heat penetration in the soil, and that I showed earlier in this chart, which clearly showed that piping buried at depths of 12 inches or greater would basically never reach these kinds of temperatures in any wildland-urban interface wildfire conditions. So again, very hot at the surface, but as soon as you get to some depth, the temperatures are really, really mitigated and not the kinds of temperatures that would produce the benzene and other VOCs. So where is that contamination coming from? Well, logically, in a wildfire, in an urban wildfire, you have uncontrolled burning of natural or artificial organic materials. Those create benzenes and VOCs. And by that I mean like trees, lumber, fabrics, asphalts, shingles, tires, plastics, gasoline, all those things that are non-metallic can produce benzene and other VOCs if they're burned in uncontrolled fashion. And obviously in a urban wildfire, there's a lot of that. In fact, burning of wood, like for your fire, is one of the largest producers of benzene in the environment. So the smoke and air in a fire is heavily, heavily contaminated with all kinds of chemicals. And the siphoning effect that occurred during the negative pressure events I described earlier would pull these contaminants into any kind of breaks in the piping system. Remember, the water was drained out of the piping during the fire, so the contaminants were able to be sucked into the system. And this probably explains why the degree of contamination was found to differ significantly through the water systems, because the piping broke differently depending on where it was. And remember, both plastic and metal piping were contaminated. So the result was that during the fire, the empty mains and surfaces were contaminated, whether they were made of plastic or metal. Now let's look at the claim about plastics releasing these chemicals back into the water. There's probably some truth here, but there hasn't been much research that's been done in this area in terms of what actually happens in a wildfire. Generally, plastic piping can be expected to absorb some of these organic contaminants into or onto the pipe wall. While it's a slow process, if the contaminants sat on the surface of the pipe for an extended period of time, as it did post-wildfire, before trying to be put back into service, then there might be enough time for some of those contaminants to be absorbed into the pipe wall. Then when water was reintroduced, those contaminants could have migrated or desorbed slowly out of the pipe wall, thus contaminating the water in the pipe. When the flow is intermittent, like a service line, there is potentially time for the concentration to increase in the water. This is quite likely what was observed in Paradise. You might say that the service line should be flushed, which was done repeatedly. But as the desorption process is slow, for service lines, they found they needed to flush repeatedly for a long time to pull all those contaminants out. This was determined to be impractical for a service line to a building due to the number of cycles and the need to get the water surface operational. So they decided to replace the pipe, all service lines. When it came to mains, the continuous water flow that you would have in a main kept the concentration within acceptable limits. So PPI recommendation I addresses the contamination, and it says flushing the water mains can be effective at reducing contamination and the VOC levels to within acceptable limits. Guidance of the water utility and local authorities should be followed. After a fire event, if a structure is reoccupied or surface is restored to any occupiable structure, water should be tested for contaminants as recommended by the water utility or local authorities. Testing should be done on a structure-by-structure basis, as contamination may appear unexpectedly within an area and may not be associated with damage to the particular structure. Flushing of small diameter service lines may not be effective or economical. In such cases, it is recommended to replace the service lines and components, regardless of the material. All service lines should be properly buried. So in summary, in a fire, trees, lumber, household goods, cars, vegetation, etc. produce benzene and VOC contaminated air and water. Plastic piping buried 12 inches or more will not likely see sufficient heat to be degraded. Contaminated air water can enter through breaks in the piping as the water is siphoned out. Systems that remain full of water are inherently protected. Benzene and VOCs can be distributed throughout the water system in both plastic and metal piping. Plastic piping may absorb benzene's VOCs and then release or desorb them slowly into the water when refilled. Flushing of service lines may not be effective or practical to remove benzene VOCs, so they should be replaced. Flushing of mains has been shown to be effective, and water should be tested per local regulations. So again, we have PPI TR 51 and recommendation I. Both of those are available on our website under the all publications.